In this lesson, we'll be talking about division of degrees into smaller parts and an introduction to the law of sines and the law of cosines, about which most of this chapter deals with. All right, so the degree can be divided into 60 smaller parts called minutes. Each minute is further divided into 60 smaller parts called seconds, very much the same way that an hour is divided into minutes and each minute divided into seconds. An angle measuring 25 degrees, 17 minutes, and 51 seconds is typically written with the notation 25 degrees, 17, and a single apostrophe, and then like an end quote after the seconds. Okay, same way that you use feet and inches, same abbreviation. All right, for the purposes of converting to degrees, minutes, and seconds into decimal form, the following conversions can be used. 1 minute is 1/60th of a degree, and 1 second is 1/3600th of a degree. If I want to calculate the decimal version of 53 degrees, 42 minutes, 36 seconds without using a calculator, I'm going to think of this in parts. I have my 53 degrees, plus I have 42/60ths of a degree. That's our minutes. They're out of 60. And then 36 3600ths of a degree for those seconds. So now I'm just going to reduce each of these fractions. We've got 53 degrees plus 42/60ths. 6 goes into both of those. 7 and 10 times plus 7/10ths plus 36 3600ths is 1/100th if you reduce that. And so that would be 53.71, 7/10ths and 1/100th of a degree. And there's our conversion. In practice, we're not really going to convert without using a calculator. I just wanted you to get a feel for what that means. All right, now we're going to convert from DMS to degrees, or DMS is a way of saying degrees, minutes, and seconds, to degrees on our calculators. Okay, so take a moment, fire up your calculator. First thing we'll do is open a calculator page in the scratch pad or in a document, and then enter the angle in DMS form using a template, which is next to the 9 key. So I'm going to do those things, home key, and then press A for a scratch pad, and then I'm going to enter using the template. It's next to the 9 key, so press that one right next to the 9 key, and we need to find the degrees, minutes, seconds template, which is over here. Press enter, and now you just enter the degrees and the minutes and the seconds in there. Let's go down to example 2. We're to convert 5 degrees, 23 minutes, 57 seconds to degrees, so I'm just going to enter my 5 in the first space and my 23 in the second space, cursor over, and 57 in the third space. And then finally I'm going to press Control and Enter, which is the way that we get an approximate decimal. And if we're rounding to the nearest thousandth, that turns out to be 5.399 degrees. All right, you try the, well, actually, never mind. We're going to try together going the other direction, 53.278 degrees to degrees, minutes, and seconds. This time we're going to round to the nearest second. In order to do so, we'll open a calculator page again, and then we're going to enter the angle in decimal form, press Catalog, and then choose Menu 3, and select the conversion symbol, which is not the regular arrow, but a little sideways triangle, and type the letters D, M, and S for degrees, minutes, seconds, which is telling us that we want to use the conversion and we want to convert it into DMS form. And then press Enter to find the DMS equivalent. All right, so let's try that example in B below. So if we're in our document, I'm going to type in 53.278, and then I'm going to press the catalog key, which is right next to that template key that we just used. And in there, I'm going to pick out in the third menu the conversion symbol. In different operating systems, this may appear in slightly different places, so you may have to search for that. But make sure that you're using the sideways triangle. Okay, and then we're going to press enter on that, and then I'm just going to type in the letters D, M, and S, and then press enter. And so we have 3 degrees, 16 minutes, and 41 if we're rounding to the nearest second. So 3 degrees, 16 minutes, and 41 seconds. All right, so if we're working with a DMS angle, then if I want to find the sine, the cosine, or the tangent of it, we're going to find that trig function, enter that, and then we're going to use that template, which is next to the 9 key, to enter the angle. All right, so let's try that. Sine of 74 degrees, 4 minutes and 23 seconds. I'm just going to take my calculator, use the trig menu to find the sine, and then enter in that template, which we found in the key next to the 9 key. And there's my degrees, minutes, seconds template. So I just enter 74 degrees, 4 minutes, 23 seconds, press enter, and we've got 0.962. All right, let's you try the next one on your very own. All right, did you get negative 0.905? Awesome. Let's move on to the law of sines and law of cosines. All right, the law of sines and the law of cosines are two formulas, I guess, that you could use for any triangle, not just right triangles. SOHCAHTOA is for right triangles. These are for any triangles. They're all stated for any triangle ABC for which side A is opposite vertex A, side B is opposite vertex B, and side C opposite vertex C. And that convention would follow no matter what letters are used to represent the vertices or the sides. Just remember that capital letters are vertices, lowercase letters are sides. Okay, so the law of sines is stated sine of angle A over the length of side A equals sine of angle B over the length of side B equals sine of angle C over side C. In practice, it won't be used altogether like that. Just 2 of the equal portions of that would be used together to form a proportion, and we can cross multiply to solve. The law of cosines is stated a lot like the Pythagorean theorem. The first version of this is c squared equals a squared plus b squared, but then there's this extra part tacked on, minus 2ab cosine c. And what I want you to notice about it is it looks a lot like the Pythagorean theorem, but we have this extra term, and notice that the angle C is corresponding to the opposite side C that's by itself on the opposite side of the equation. We can use this with any side. It doesn't matter what C, A, and B are. They don't have to be the longest side. They don't have to be the shortest side. So you can see 3 different statements. The second statement is stated with b squared all by itself. So that would be equal to a squared plus c squared minus 2ac cosine b. And then finally, the third version with a squared by itself. When we're using the law of sines, as we said, 2 of those ratios are used to form a proportion. When using the law of cosines, we only use 1 of the 3 variations. All right, so for each triangle, we're going to use this given information to write an equation that could be used to solve for an unknown side or an angle. And we're not to solve the equation, just to write it. So in the first example, we have a triangle ABC, that side A is opposite angle A, and so on for the other vertices. Let's label the measures that we know. Angle B is 64 degrees. Side B is of length 9, and measure of angle C is 38 degrees. Now what we're to do is to write an equation that could be used to solve for A. What I want you to notice is that we have 2 sides and 2 angles. This is going to indicate that we probably want to use the law of sines, since that involves 2 sides and 2 angles. The downside to using the law of sines here is that we don't have the angle that's opposite side A to use. Or do we? Remember that measure of angle A has to be 180 minus the 2 other angles of the triangle, which gives us 72 degrees. So now we can write a proportion. Sine of 72 degrees over its opposite side A equals sine of 64 degrees over its opposite side 9. Notice that there's only one unknown in this proportion, and so it could be solved for A. All right, in B, we'll draw a triangle XYZ. Remember, this triangle does not need to be drawn to scale. Now let's label the known sides and angles. Remember that opposite sides are used the same letter as the opposite angle. And so we are looking for sidewise measure, which is opposite angle Y. All right, notice this time we have 3 sides and an angle. That's going to indicate that we need to use the law of cosines. Since we have both side Y and angle Y as a variable and a known, let's use the version with y squared by itself on one side. Remember that it starts out like the Pythagorean theorem, y squared equals x squared plus z squared. Extra term minus 2 times x times z times cosine of angle y. And now all we need to do is replace x with 16, z with 11, and the measure of angle y with 127. All right, let's try one more in C, triangle BAM. And this one has side measures given of 7, 8, and 10, and we're looking for angle A. Notice again, this one has 3 sides and 2 angles. 3 sides and 1 angle mentioned. This would imply that we're going to use the law of cosines. We'll need to use the law of cosines that pairs together the opposite side 8 and A, the unknown angle. 8 squared equals 10 squared plus 7 squared minus 2 times 10 times 7 times the cosine of angle A. Again, notice in the law of cosines how 8 is the side that's opposite cosine of angle A, or 8 is the side that's opposite angle A, and they are on opposite sides of the equation. All right, try D on your very own. All right, did you get the proportion sine of 25 over 6 equals sine of angle K over 9? That would use the law of sine since we have 2 sides and 2 angles mentioned. All right, let's try E together. In E we have triangle EFG, and we have 2 angles and 2 sides mentioned. Let's fill in the measures of the angles as well as the sides, and you'll notice that despite the fact that we have 2 sides and 2 angles, we don't have pairs of opposite angles and opposite sides. But since we have 2 angles, we can find the third angle by subtracting the other 2 from 180 to get 81 degrees. So sine of that angle, 81 degrees, over its opposite side G equals sine of 70 degrees over its opposite side 19. Notice that we did not use the 29-degree angle because we don't have an opposite side labeled with a measure or with a variable. Try H on your very own. All right, for this one you should have used the law of cosines since we have 3 sides and an angle, and we'll choose the law of cosines where q squared will be by itself on one side of the equation since we have angle q on the opposite side of the equation, and angle q is opposite side q. Okay, this next example is going to give us some experience solving the law of sines or the law of cosines using some familiar angles. So in A, we have sine of 30 over side A equals sine of 135 degrees over 6. We can know the values of sine of 30 and sine of 135. Before we plug in those values, though, let's cross multiply. So we should have 6 times the sine of 30 equals A times the sine of 135. 30 degrees is a first quadrant angle. We can draw our 30, 60, 90 triangle, and sine will be opposite over hypotenuse, or 1/2. Now to find the value of sine of 135, which is a second quadrant angle. 135 is 45 degrees more than 90, or 45 degrees less than 180. Either way, we get a 45-degree reference angle. And the sine of 135 is 1 over root 2. For the moment, I'm going to leave that expression unrationalized. Simplifying both sides of the equation and multiplying by root 2 gives us A equals 3 times the square root of 2. Now let's tackle B, but before we evaluate each trig value, let's cross multiply. We'll get 2 times the sine of 60 equals 2 root 3 times the sine of a. Now let's evaluate the sine of 60 degrees. 60 degrees is a first quadrant angle. We can draw a 30, 60, 90 triangle and find that sine of 60 is square root of 3 over 2. I'll bring down the other side of the equation since we don't know the sine of angle A. Simplify the left side of the equation and divide by 2 root 3 to get sine of angle A equals 1/2. Now we need to solve the equation, remembering that our angle can be anywhere between 0 and 180 degrees. Since sine is positive in both the first and the second quadrants, we'll get 2 solutions. Drawing 2 reference triangles with an opposite over hypotenuse equal to 1 over 2 give us 30-degree reference angles, which means that measure of angle A may be 30 degrees or measure of angle A equals 150 degrees. This is a good example of what we'll call the ambiguous case when we study law of sines in greater depth. All right, now let's try one with law of cosines. In C, we have a squared equals 16 plus 4 minus 16 cosine of 120. We can do some of the arithmetic. 16 plus 4 is 20, and then we can find the cosine of 120 and multiply it by 16. If we draw a 120-degree angle, its supplement 60 is the reference angle. Its adjacent side is negative, and so cosine of 120 is negative 1/2. Performing the further arithmetic, we get a squared equals 20 plus 8, and if a squared equals 28, then a equals 2 root 7. All right, try D on your own. All right, you should have gotten measure of angle A equals 60 degrees. This one has some algebra in it that's a little bit tricky. What you have to remember is that you cannot subtract 5 minus 4 before multiplying by cosine A. So you have to actually just subtract 5 from both sides first and then divide by negative 4 to solve for cosine A. If cosine A is equal to 1/2, then angle A has to be 60 degrees for an angle that's between 0 and 180, because in quadrant 2, angles greater than 90 have a cosine that is negative. All right, let's try E. So let's cross multiply first, and a 120-degree angle gives us a 60-degree reference in quadrant 2, giving a sine value of square root of 3 over 2, and 30 degrees is a quadrant 1 angle, giving us sine of 30 is 1/2. Simplifying both sides of the equation, and multiplying by 2, and finally dividing by the square root of 3, and rationalizing, we'll get b equals 10 root 3 over 3. We're going to save the last 3 examples for class, or our next class. That's it for the lesson.